Ideas. Today we can see some results on compact sets, connected sets. The first result, an open cover of a metric space X. We mean a collection G alpha of open subsets of X such that E covers union alpha G alpha. So open cover E of a metric space. So for example, I am taking minus n comma n. Okay, the collection G alpha is equal to collection of open subsets of X and A. So in the real life we can see if I put n belongs to natural numbers, here you can see minus 1 comma 1. Okay, the open set. Then here minus 2 comma 2. Similarly minus 3 comma 3, so on so on. So this gives what? Collection of open set. This is one of the open set, this is one of the open set, this is one of the open set. So whose union, okay, that covers what? Minus n comma n. Okay, so union, that arbitrary union of collection of open sets that covers the set, we can say that that is said to be the open cover. എല്ലാ ഓപ്പൺ സെറ്റും കവർ ചെയ്യുന്നുണ്ടോ മൈനസ് എൻ കമ്മ എൻ, അതുകൊണ്ട് തന്നെ ഓപ്പൺ കവർ എന്ന് പറയും. So what is compact? So compact means if every open cover contains a finite subcover, ഒരു open coverന് finite subcover ഉണ്ടായിരിക്കും, that we can say that it is a compact set. So for example, you can in notation you can say that it covers union I is equal to 1 to n of G alpha I. ഇങ്ങനെ ഉണ്ടായിരുന്നെങ്കിൽ we can say that that is said to be the compact set. So for example, I am taking one compact set is minus n comma n with n belongs to n. Now I am taking the subcover as G alpha dash is equal to set up for minus 2n comma 2n, right, with n belongs to n. N belongs to n. So in this real line you can see that this when if you put n equal to 1, you will get here minus 2 comma 2, and n equal to 3 you will get, sorry, n equal to 2 you will get minus 4 comma 4. Similarly minus 6 comma 6, so on so. So from this you can understand that this open cover has finite subcover. Okay, this has finite subcover, this covers this one. Okay, open cover contains a finite subcover, then we can say that that is a compact set. You can see some results. Compact subset of a metric space are closed. Similarly, closed subset of the compact sets are compact. So compact subset of a metric space, compact subset of the metric space is closed, and the closed subset of the compact metric space is compact. Then F is closed and K is compact, then F intersection K is compact. Or you can see that intersection of closed and compact set is compact. The intersection of closed and compact is compact. Then the next result, K alpha is a collection of compact subsets. If you take K alpha is a collection of compact subset, then the intersection of finite subcollection is non-empty. If it's so, then intersection K alpha is also non-empty. So if you select K alpha is a compact set and then intersection of finite collection is non-empty, if so you can write that intersection arbitrary intersection of K alpha is also non-empty. So in this case K alpha is a collection of compact set. If it is for the collection of intervals or the collection or the sequence of K cells, means also the condition is true, that is intersection K alpha is non-empty. Then seventh one, every K cell is compact. Eighth, if a set E in Rk has one of the following property, then it has the other two. If E is closed and bounded, then E is compact. So this is Heine-Borel theorem. Heine-Borel theorem. So if E is closed and bounded, definitely that set is compact. Then E is compact, then every infinite subset of the E has a has a limit point. So this is one of the result. Every infinite subset of the compact set, because here it is given E is compact. So every infinite subset of the compact set has a limit point. Then ninth one, every bounded infinite subset of Rk has a limit point. So this is Weierstrass theorem. This is Weierstrass theorem. Every bounded infinite subset of Rk has a limit point in Rk. Then 10th one, let P be a non-empty perfect set, then P is uncountable. So perfect set, we already seen that it is closed. That is, a set is closed and every point of that set has a limit point. So for example, if I am taking E is a set, closed set, it is closed and every point of that set has a limit point. So that is perfect. So that we can say that that type of uncountable. So the 11th one, using that itself, we can write that P is a perfect set which is closed. So closed interval, the condition is A less than B is uncountable. Then set of all real numbers is uncountable. Then contour set is uncountable. So contour set means you have to start with the 0, 1. So Cantor set. So 0, 1 is divided into two portions. That is 1 by 3, then 2 by 3, then 3 by 3 is 1. Now you have to remove the middle one so that the next one is 0, 1 by 3. Then the next portion is 2 by 3, 1. Then again you have to divide it into 3 segments. Here also you have to divide it into 3 segments. So if it's so, you can see that it consists of the union of 2 power n intervals. You can see in the Cantor set the 2 power n intervals. First you can see how many interval 1, then 2, because we are leaving this middle one. So 2 square. Okay. So 2 square is 2 power 1. So 2 intervals. Again here you can see that you are leaving this middle interval, again this middle interval, so that you will get 1, 2, 3, 4. So that 2 square. So that Cantor set has the union of 2 power n intervals. So Cantor set is uncountable. Similarly, we can say closed interval 0, 1 is uncountable. Now we can see connected sets. So two subsets A and B of metric space S are said to be separated. If the two subsets are separated, means the condition is A intersection B bar and A bar intersection B are empty. Both. This both should be empty. So for example, you can say, see this A is equal to closed 0, 1 and the another one subset I am taking B is equal to 1, 2. So now we can see the condition. A bar is equal to the same closed 0, 1. B bar is equal to closed 1, closed interval 1, 2. Now we can check A intersection B bar, which is equal to A is here 0, 1, closed 0, 1, and intersection B bar, which is closed 1, 2, which is equal to, you can see the intersection is 1. Now we can see another one, A bar intersection B. The next condition. So A bar is 0, 1, intersection B is 1, 2, which is equal to empty. So according to the separated condition, both this condition should be empty. So here you can see that it is not, both are empty, so that this is not separated sets. Okay. So we can say that these two are not separated sets. So if it is not separated, then we can say that is connected. That is the 15th one. A set E subset of X is connected if E is not a union of separated sets. So if it is not a union of separated set, then we can say it is connected. So this example is a connected set. We see in this one, it is not separated, so it is connected sets. The next one. If A and B are vessels, if A and B are connected subsets of a metric space and A intersection B not equal to empty. See this one, A and B are connected and A intersection B not equal to empty. If so, A union B is connected. Then R is a connected set. Then R is a connected set. And one more, here R is not compact. That we have to see R is not compact, because it has open cover. For example, minus n, n. Okay, with the n belongs to natural number. So minus infinity, infinity. So it has open cover, but it has no finite sub cover to covering this one. So that it is not perfect. So here it is connected for the connected case. Then subspace of R is connected if and only if it is an interval. So if the subspace of R is connected, then we can say that that is an interval. Or interval means also it is connected. Continuous image of a connected set is connected. And the last result is subspace of a connected space is not connected. Subspace of a connected set is not connected. Thank you.